Hello friends, we will discuss the important special purpose diode, that is photodiode. Let us see the principle of operation of photodiode. We have simple p-n junction here. This is p side, this is n side, and we have the window at the junction like this, which is illuminated. This is light. Right, the window at the junction is illuminated like this. We have a reverse bias diode. Diode is reverse bias here. This is reverse biasing voltage. Say voltage across the diode is V, current through the diode is I. Fine. So if it is reverse biased, let us see how it is going to operate, how it is going to behave. When the junction of this PN diode is illuminated, it will result into generation of electron hole pairs in the junction area. These are nothing but the generation of electron hole pairs at the junction area will result into movement of electrons from p side to n side. Why? Because this is positive. If it is positive, electrons will be attracted from p side to n side. It is negative, electrons will be diffused from jumping from this side to this side, from n side, that is electrons will be jumping from p side to n side, and holes will be jumping from n side to p side. I repeat, it is positive, it is negative, it will attract the electrons. So when it is this area is illuminated, electrons will move from this side to this side, that is from p side to n side of the junction. Similarly, holes from n side to p side. Why? Because holes will be moving from n side to p side, because it is negative. So when you increase intensity of the light, more and more electron hole pairs will be generated. Remember, the number of electron hole pairs generated are directly proportional to intensity of the light. Fine. So more is the intensity, more electron hole pairs are generated, more will be current in the circuit from N to P. Current will be flowing like this. Fine. So if you talk about the current in the circuit, the diode current is nothing but I naught, simple diode current, that is I naught e raised to power V by eta Vt minus 1. Fine, but V is what? Minus VR here. It is minus VR. And there is one more component of the current. I is equal to minus I photo. Why I am saying Y photo? It is called short circuited current as well. Why it is minus? Because symbolically I am taking current from P to N. In normal case, the diode current is taken from anode to cathode. This is anode, this is cathode. Diode current symbolically is from anode to cathode, but because of illumination, there are holes jumping from N to P side. So optically generated current, that optically generated carriers are moving what? Optically generated holes are moving from N to P side, electrons are moving from P to N side. So the optical component of the current is moving from N to P side. That is opposite to Y. So I am taking minus sign, right? Plus I naught e raised to power V by eta Vt minus 1. That is the current in the photodiode. Fine. So this is very important relation, where what is this ISC? ISC is called short circuited current. What do we mean by short circuited current? If you short this component, V will be 0. If V is 0, it will be 1. 1 minus 1 is 0. So this will be short circuited current. It is also called, its another name is photocurrent. That is known as photocurrent. And that is also known as optical current. It has got three names. Symbolically, it is denoted by I photo. Symbolically, it is denoted by I optical in different books, but it is same current. It's not different. Optical current Then photocurrent, short circuited current is the same thing in photodiodes. Fine. That is, if you draw the VI characteristic of photodiode, and it is short circuited current is what? Because of the jumping of holes from these holes here are what? Magnetic carriers. Jumping of holes from this side to this side, jumping of electrons from p side to n side. So that means the short circuited current or photocurrent is because of the jumping of optically generated minority carriers across the junction. Please do remember, the photocurrent is what? The current due to jumping of optically generated minority carriers across the junction. Fine. That is nothing but short circuited current or photocurrent. Fine. So there can be question on this. If you talk about this component of current, mathematically that can be given as the optical component of current is A, Q, then access carrier concentration P, then tau A into, that is A into L. It is like this. Let us see how it is happening. Please see that. A into L into, not L, rather W you can say. Let us see how it is happening, how this current is coming into picture. Fine. So the basically this is what? This is the number of holes generated, additional hole generated per unit volume, and this is, I'll give the expression of current here. I'll just discuss this. That is the component of current. I'll discuss this component of current. I'll discuss it. Let us how it is going to happen. When the junction is illuminated, there will be generation of electron hole pairs at the junction. Fine. These electron hole pairs are moving across the junction. Holes are moving from n side to p side. Electrons are moving from p side to n side. Fine. So there is something called a generation rate, optical generation rate. That optical generation rate is nothing but del P by tau P. That is rate of generation of access carriers because of the illumination per unit time. That is rate of generation. Fine. So at which this, if you find the total carriers generated in the junction area, say this is W, how can we find the rate of generation of the charge carriers? You know, that is G. So if you can find the rate of charge generation will be what? Your optical current. Rate of generation of the charge will be equal to, this is G, that is rate of charge generation. Rate of charge generation will be equal to A, that is equal to area multiplied by this, that is volume. The G is what? G is number of holes generated per unit volume. If you multiply this by volume, so that becomes charge generated per unit volume. So this is G into OP, GAW, G into OP. That is charge, that is GOP is what I am repeating. GOP is the number of charge carriers generated per unit time. The number of charge carriers generated per unit time multiplied by volume. Volume of this A is area of cross section of the junction, W is width of the charge carriers generated in the junction area. So volume of the junction area multiplied by rate of generation. Rate of generation is nothing but number of charge carriers generated per unit volume. So this becomes nothing but total number of carriers generated per second. I repeat, G is number of charge carriers generated per unit volume multiplied by divided by time. So G is nothing but number of holes generated per unit volume per second. If you multiply it by volume, so that becomes the number of holes generated per second. So number of holes generated per second is nothing but GOP multiplied by volume of the junction. So, and if you multiply by charge of each hole, so that becomes charge generated per second, and charge generated per second is nothing but that is your short circuited current AWGOP into Q. This is your short circuited current. But here there are two additional components. What are the additional components? There are two additional components of current. If generated in P and N layers within diffusion length from junction are also diffusing through the junction, then the short circuited current will be nothing but G, that is ISC will be equal to, everything will be similar, AWGOP, but that will be AQGOP WLN plus LP. Again, please understand the meaning of this. I am repeating the whole concept again. G is what? The number of access carriers generated per unit volume per second. The number of access carriers generated per unit volume per second. If you multiply it by volume, that becomes number of access carriers generated per second. So multiplied by volume, that becomes number of carriers generated per second, multiplied by charge of each carrier, so that becomes charge generated per second. That is the current, optical current. Charge generated, additional charge generated is nothing but responsible for the optical component of current. But if the charge carriers are also generating in this region, that is LP and that is LN, these are generating in this region as well, we will take those carriers also into consideration, because these will be diffusing through the junction, and we are taking this, not only this volume, rather this volume. So in this total volume, that is the depletion layer, and then up to the diffusion length on P side, up to the diffusion length on N side, so that is nothing but short circuited current or optical current. Fine. Although there was no question on this concept, but just to let you know that that component of current which we were talking about is this component of the current. Fine. Now this is optical component. Let us talk about VI characteristic. VI characteristic of photodiode. So we have just seen your photodiode works in which mode? In reverse bias mode. In normal case, when there is no illumination, in reverse bias there is small current that is equal to reverse saturation current. There is no illumination, so there will be reverse saturation current. When there is no illumination, that reverse saturation current now is known as dark current. So this is nothing but dark current. So reverse saturation current of a photodiode is called dark current. It's nothing else. There was question on this. Okay, dark current is what? Reverse saturation current. Fine. When you start illumination, so what will happen? This diode current will start increasing. The diode current will start increasing like this. So what is happening? This is short circuit current IC1, ISC2, ISC3. So the reverse saturation, component of current which was short circuited current is increasing with intensity of light. So more is intensity of light, more will be the short circuited current in case of the diode. So this is called reverse saturation. This is called VI characteristic of photodiode. So what do we observe here? The diode current increases with increasing intensity. A photodiode works in which quadrant? Third quadrant of VI characteristic in reverse bias mode. That is the question. Fine. What do we observe? I am able to sense the light with photodiode. When there is no light, it is just like an open switch, current is negligible. When it is illuminated with light, current is flowing, so it is sensing the light. So photodiode can be used as a photo detector. Fine. So photodiode is nothing but a photo detector. There is one more concept here. There is something called avalanche photodiode. Avalanche photodiode is what? That is nothing but when you illuminate the light, there is generation of electron hole pairs. When these electrons move in the depletion layer, these will be colliding with the semiconductor atoms, and these will bring out another electron. That is called impact ionization. So the diode which works on the principle of impact ionization due to optically generated electron hole pairs, that is called avalanche photodiode. So it is basically the mechanism of operation of the device, nothing else. Otherwise it is same thing. Fine. So avalanche photodiode works on the principle of what? Impact ionization by optically generated electron hole pairs. That's it. Fine. So this light is working like what? Light source here is working like minority carrier injector. It is injecting the minority carriers from N to P side and P to N side. Remember, it is minority carrier injection only. So your source of light is nothing but minority carrier injector here in this case. Now let us talk about the another important concept, that is nothing but important terms rather used in photodiode, that is called responsivity. Responsivity is the term used in photodiode. Responsivity. Responsivity of the tunnel diode R gamma or R lambda is defined as the photocurrent. This is photocurrent per unit incident power. So this is P is what? Optical, that is incident optical power here. Fine. That is incident optical power. So this is your responsivity. So if you are given responsivity, you are given incident optical power, you can find the photocurrent or short circuited current of the diode. So responsivity is basically the ratio of photocurrent to the power of incident light at a particular wavelength. Fine. So then there is another important term used in photodiode, that is known as quantum efficiency. Please do remember, that is quantum efficiency. These terms are important for GATE exam. There are numericals based on these terms, quantum efficiency, then responsivity. Fine. So quantum efficiency of a diode is defined as, that is Q is quantum efficiency is defined as the ratio of charge. Basically the quantum efficiency is the ratio of fraction of incident photons that contribute to photocurrent. It can be defined as the number of carriers collected at the junction for every photon impinging on the photodiode. It means basically it is giving the number of charge carriers per unit photon. I repeat, quantum efficiency is the number of charge carriers received at the junction per unit incident photon. Mathematically it is given by, that is nothing but current of the your diode IOP by Q divided by the power, optical input power, by H nu. Nu is frequency of the light. This is important for exam. H nu is energy of incident light. Fine. P is what? Optical power of incident light. Fine. Nu is what? Frequency, and nu is nothing but that is C by lambda. C is speed of light. Where? Speed of light in photodiode. Fine. So there can be a question on this mathematical relation, and you just need to remember rather than driving the expression. These are given directly in textbooks as well. Fine. So there can be question on quantum efficiency, then responsivity, and there is another third important concept here that is to be remembered. You should remember the photocurrent. Photocurrent or short circuited current of the photodiode is same thing. So that note has to be remembered. The photocurrent is directly proportional to intensity of light. Remember this. Fine. So if IV is intensity of light, then the I photo or I short circuited current is equal to some constant K multiplied by IV of proportionality. Remember this. This K is constant of proportionality. So there were questions in past that intensity of the light is increased 10 times. So what will be the short circuited current? What will be the photocurrent? It becomes 10 times. If intensity is increased 20 times, the current becomes 20 times. So the photodiode, your photocurrent of a photodiode is directly proportional to intensity of the light impinging on the junction of the diode. Fine. Another important point, if you increase the distance of the source from the junction, this is distance of source from what? From junction, then the photocurrent will be maximum when it is closest to the junction, and it will decrease non-linearly when you move away from the junction. That is the sort of bell curve. Fine. Then let us talk about applications of photodiode. Applications of photodiode. Very first application you can see, that is it is used in as a light detector or photo detector. Then second application, it can be used for reading of the film track. Third application, it can be used for counting of the objects on a production line. When you are having source on one side, then detector on side, when object passes through, there will be break and that pulse can be counted. So counting of the objects on production line. Then high speed reading of the computer punch card, photovoltaic cells, and so on. These are some of the applications of photodiode, and we will see the numericals on photodiode at later stage. Till then, just wait for my next video. In my next video, I will be talking about photovoltaic or solar cell, and after that we will see the numerical part. Thank you.